All right, so welcome back. I hope everyone's having a good fall break. So here's kind of where we were at the end of Wednesday. We were looking at the parametric Bessel function, so x squared times the second derivative plus x times the first derivative plus alpha squared x squared minus n squared times y equals 0 for n equals 0, 1, 2, and so on. Okay, so alpha here was our parameter. And we know the general solution of the parametric Bessel function is C1, or constant, times Jn of alpha x plus C2 times the nth Bessel function of the second kind at alpha x. Okay. Now here it turns out that we're going to be on an interval, or a closed interval, 0 to b. Well, it turns out that the y sub n, the Bessel functions of the second kind, all blow up at 0. Okay, so the relevant solution, or the relevant functions that we're going to consider, are just constants, so I'll just say Jn of alpha x times a constant. Okay, so these are the solutions to this equation, or in other words, they're the eigenfunctions of an associated Sturm-Liouville operator. So let me just put this here. So in Sturm-Liouville form, or I could put the Bessel function in self-adjoint form. So this would be x, y double prime, just divide everything by x, plus alpha squared x minus n squared over x, y is equal to 0. All right. So the relevant, or the most relevant thing in this expression is that this is our parameter. So this is our p of x. Okay. And what we would like, what we want, and what we worked out a bit last time, was we want an orthogonality relation between the different eigenfunctions. Okay, so of course, but they're going to involve this weight p. So the different eigenfunctions were of this form, alpha ix, alpha jx. Okay, so this is the orthogonality relation that we want for different eigenvalues. And we worked out that this wouldn't be true in general. We needed specific boundary conditions. Okay, and the relevant boundary conditions. So the relevant boundary condition was that a constant times the Bessel function at alpha, not alpha beta, alpha b, plus b times, well now alpha times the alpha nth Bessel function of alpha b was equal to 0. Oops, sorry, and this is a derivative. And that's precisely why we have this extra term alpha. That's because we're taking the derivative of alpha x and using the chain rule, so we get an extra alpha term. Okay, so that was the boundary condition. It was only at b because we had a function r, which was just r of x equals x. Since r of 0 was equal to 0, that gave us that you didn't have to have any boundary condition at 0. Okay, but at b, you have to. So maybe I'll just say here what we're going to want now. So the next step is we want to have a Fourier-Bessel series. Okay, so what this means is that we want to have a function from the closed interval to r, and you want to write it just as the sum of Bessel functions that are weighted. Okay, so we want to write it as the sum from 1 to infinity, or I equals 1 to infinity, ci times the nth Bessel function at alpha ix. Okay? Now, this should remind you very much of Fourier series, where we were looking at the one-dimensional wave equation, and then we looked at the sine function, and we were looking at sine of nx. right? That was writing, a random function f of x as a weighted sum of sines. So here, this is replacing the sine function just with the Bessel functions. The reason we do that is because, well, the Bessel functions are solutions to this Bessel equation, which turn out to have, as much physical significance as the solutions to the one-dimensional wave equation. Okay, so we'll see all of this coming up, but this is what you would like. You want to write a general function as a sum of solutions to a certain differential equation. Okay? Of course, what you would also like is not just, this is part of Fourier series, but you also would like to know what the coefficients are. So we would like to have a formula for, the C sub i's. Right? So we want a formula, and of course we know what it should be since we have this orthogonality relation. Okay, so C sub I should be the integral from 0 to b of x times the nth Bessel function of alpha ix times f of x over the norm of the nth Bessel function at alpha ix. Okay? Oh, sorry, the norm squared. And one thing to note, since we're going to get these coefficients using this orthogonality relation, this orthogonality relation is with respect to the inner product. So let me just put here, when I take the norm, this norm has to be, again, taken with respect to the same inner product. So when I write this is really the weighted inner product of x, or so it's x times the nth Bessel function squared of alpha ix dx. Okay? So when I write this expression, of course, this is just this weighted norm with f weighted by x over the inner product, weighted inner product again, of the Bessel functions. So it is all the usual formulas, except that the inner product is weighted. Okay, that's the difference. So let me make a note here, though, an important remark, which will occupy us for a while. So note that the boundary conditions, so the choice of boundary conditions. Okay, so let me just pull this up here. So we have a choice here, right, on what A and B are allowed to be, okay, and choosing different values for A and B will give us different boundary conditions. The choice of these boundary conditions influences the alpha i's, so it influences this choice, alpha ix, and hence influences the norm. Okay, so it influences what eigenfunctions you choose, and hence influences the denominator. Of course, it also influences the numerator, but let me just stick with the denominator for now. Okay, let me do an easier example. Okay, going back to the one-dimensional wave equation, our favorite example. So here we have the second derivative of y plus lambda squared y is equal to 0. Instead of doing this on the interval 0 to pi, let me do this on the interval 0 to 1. Okay, it just makes it a little clearer in this case. And then the usual boundary conditions would be that y of 0 is equal to y of 1 is equal to 0. So this would be the case if we were on a vibrating string set at 0 and 1. And we know that we would get solutions of the type, well, a constant times sine of n, or pi, n x, for n equals 0, 1, 2. Okay? So that's a perfectly good Sturm-Liouville equation, perfectly good boundary conditions, and we get an orthogonal set of functions. On the other hand, there's a bunch of choices for the boundary conditions, and so another example could have been So I could have chosen y of 0 being 0, and then say y of 1 plus the derivative at 1 has to be equal to 0. Okay, that's just another thing you can do. All right, and we'll see that you get completely different eigenfunctions. So here, the fact that your y of 0 is 0, well, the general solution for this equation is a constant times sine of ax plus a constant times cosine of ax. The fact that y of 0 is 0 still tells you that you're dealing with some multiple of sine of ax. Okay, that's what you're forced into. On the other hand, what does this second boundary condition now tell you? Well, it tells you when you plug in 1, so you get sine of a. Remember, I'm trying to, well, I guess here I technically have, again, I have a constant here, but I'm going to ignore that just for a second. The sine of a, sorry, because I'm plugging in 1, and then I'm taking the derivative, so I'm getting a cosine of a is equal to 0. Okay, so that's what my second boundary condition says. That's the values of a that I spit out, and what I get is that, well, let's see, so I'm taking minus sign, so a is equal to minus the tangent of a. So these are the new eigenfunctions. Solutions to this wave equation with this boundary condition are now sine of ax for this a. Okay. Okay, so a satisfying, it's the a is equal to minus tangent of a, which you can check has plenty of real solutions. Those are the values of a that you're allowed to put in and to get solutions to this wave equation with these boundary conditions. Okay? Okay, so you can check that these are orthogonal. Okay, but you get vastly different Fourier coefficients. Okay, so the moral is that the choice of boundary conditions here will influence the eigenvalues of the eigenfunctions, and therefore will influence the coefficients here. Okay? Now here I think it turns out that the norm isn't changed when we do it for the Bessel function and we look at different boundary conditions. The norm will also happen to change, and that's what we want to figure out next. Okay, so let's do this. Okay, and it's a calculation, which I won't do completely, and it uses some clever tricks. It's all in 12.6 in your book. Okay, so let me just start. So y is going to be jn of alpha x. And we know that this is a solution to this differential equation in self-adjoint form. Okay, and what we want to do is figure out how the boundary conditions influence the norm. So we're going to do a trick here, which is that we first multiply both sides by, multiply by 2x times the derivative of y on both sides. Okay, so that's kind of a strange thing to do. Okay, but let's just see what we get. Well, so you get 2xy prime times the derivative of the product plus, we'll put this here, alpha squared x, n squared over x, 2x times the derivative of y is equal to 0. Okay, so why do you do that? Well, notice the first part here is just exactly the derivative with respect to x of the function x times the derivative of y squared. Okay, so this is just the chain rule, okay, applied to the function x times the derivative of x, or derivative of y with respect to x. So what do you do in the chain rule? Well, you have a function squared, so you would take 2 times that function, right? The 2 comes down, so you get 2 times the function. That's here, and then you multiply it by the derivative of what's inside. Well, that's there. Okay, so these are the same things. Okay. The second nice thing that happens is that we're going to bring the x in, so we get an alpha squared x squared minus n squared. And now, again, we have a 2 times the derivative of y times y. This is exactly just the derivative of y squared. Again, by the chain rule, you're taking 2y. Again, the x isn't here, so it's just 2. So this is 2y prime y. You exactly bring down the 2 and multiply by the derivative of what's inside. Well, that's y prime. Okay? All right, and now we want to figure out, eventually we want to look at the norm of something, which is an integral from 0 to b. Here we have an expression equal to 0, and what we're going to do now is integrate from 0 to b. Okay, so we integrate the whole thing. Okay, I won't do a new line, I'll just put this here. Okay, so the integral from 0 to b of this whole expression. Okay, so what happens here? Well, the first part is easy, right? The first part, when I integrate this, is just xy prime squared from b to 0. Okay, I'm integrating the derivative of a function that I know how to do. Okay, so how about the second part? Oh, no, okay, so I should say this is from b to 0. So the second part is we're looking at the integral of a product of functions. Okay, I guess I'll write it out again. We're writing a product of functions, and one of them is the derivative of something. Okay? So again, this is just exactly the time when you should be doing integration by parts, right? You have a u and you have a dv. So u dv, okay, so this is, let me write this out again. So I have xy prime squared from b to 0. Then I get uv, but I know what v is. It's just y squared. So I get alpha squared x squared minus n squared y squared from b0. And finally, I have v du. So I get the integral from 0 to b of y squared, and then 2x alpha squared. Okay, so maybe now that I've written it, let me just erase, if I can erase, just to pull out the 2 alpha squared. I get minus the integral, minus 2 alpha squared times the integral from 0 to b of xy squared dx. Okay, and this is equal to 0, which, now this looks kind of like a big mess and we've done calculations for no reason. On the other hand, notice that here, so this integral is exactly the norm that we're interested in, right? So y is the nth Bessel function evaluated at alpha x. We're interested in this weighted inner product of the function squared times x, and that's what we have here, okay? So now let me plug back in for y. So we get 2 alpha squared times the integral from 0 to b of x times our Bessel function squared dx. So this is equal to x times alpha times the derivative of alpha x squared plus alpha squared x squared minus n squared times the Bessel function squared, okay, evaluated from b to 0. And now we have to use a fact, so we use a fact about Bessel functions. So we use a fact that the nth Bessel function at 0 is equal to 0 for n greater than or equal to 1. Remember, the 0th Bessel function kind of looks like cosine, and the nth function kind of looks like sine, and all the remaining, or sorry, the first Bessel function looks like sine. All the others end up evaluating to 0 for 0. And when I plug in n equals 0 and evaluate this expression at x equals 0, everything drops out, right? So if n is 0 and x is 0, everything is 0. Otherwise, the Bessel function at 0 is 0. So it turns out the entire expression is always 0 when you plug in 0, and you only have to care about plugging in b. So we end up with 2 alpha squared, the integral of the Bessel function squared, is equal to, well, plug in b, so I get alpha squared b squared, the derivative at alpha b squared. Okay, that's the entire derivative function squared, plus alpha squared b squared minus n squared times the Bessel function squared at alpha b. Okay, which is still a not the nicest expression, but something reasonable at least, especially since we end up having relations between the derivative of a Bessel function and the Bessel function itself. Okay, so let me do some special cases now. Okay, so I'll do like case 1. I'm not sure if I'll do every case, as I said. So the first boundary condition that we could reasonably choose, we have the sum of a Bessel function and its derivative. Well, it's reasonable to assume just that the nth Bessel function at alpha b is equal to 0. Okay, so that's when you assume that the coefficient in front of the Bessel function is 1, and the coefficient in front of the derivative of the Bessel function has coefficient 0. Okay? All right, and now, well, it turns out that there are infinitely many alpha I satisfying the nth Bessel function plug up, not beta, alpha IB is equal to 0. This is because the Bessel function has infinitely many zeros. Again, you should think of these Bessel functions as analogous to sine and cosine. There, the zeros are evenly spaced. If you're at a sine function, then it's just integral multiples of pi. Here, it's something different, okay? But you still get an infinite number of terms that you plug in, and you can get 0. Okay, and these will all end up satisfying the boundary condition, and the boundary condition determines the alpha I. Okay? So what this implies is that the eigenvalues, okay, are, say, lambda I being alpha I squared. Okay? And this is precisely, let me just say, alpha I is xi over b, where xi is a root of Bessel. Okay, so in other words, Jn of xi is equal to 0. Okay, so there are infinitely many of them. We're multiplying by b, so we just have to divide by b, and then we'll plug in and get 0. Okay, so what is our norm in this case of these Bessel functions? Well, we've chosen it, right, so that these, by our boundary condition, these terms are all 0. So therefore, we can work out what the norm has to be. So you get that the integral of x times the Bessel function, and now we know that this is of alpha ix. Okay, so we have chosen specific alpha, or alpha I, which give this relation. Okay, so this is equal to, let's see, so we divide by alpha squared, so we get b squared over 2 times the derivative of alpha I b quantity squared. Okay, and this is equal to our norm that we're interested in. Okay, so now, this is a perfectly good description of what the norm is. Okay, I should say usually what people do though is not have it in terms of the derivative of the nth Bessel function, but they use a relation that we've seen before in class about derivatives of nth Bessel functions and n plus first Bessel functions. So let me just say this here. So really the j sub n prime, so what this is equal to, and you can see this, I won't prove this or anything, but it turns out to be equal, of x is equal to n jn of x over x minus jn plus 1 of x. Okay? So notice here, we're plugging in something with alpha I b. I guess it's important to point out that when I plug this into the nth Bessel function, I get 0, but of course here I'm plugging it into the derivative of the nth Bessel function, so I don't get 0, which is good, so I don't get a silly answer. So in any case, if I make this substitution, I'm going to plug this in and square it. But notice here, I'm going to be plugging it into a number where I'm plugging in alpha IB, and alpha IB, when I plug it into the nth Bessel function, is equal to 0. So this term will drop out, and you end up with exactly b squared over 2 times the n plus first Bessel function squared of x. Okay? So, of alpha IB. Okay, so these are equal in this case, but usually it's given in this form. All right, so that is the formula for the first boundary condition. We get this norm for the eigenfunctions that we're interested in. Okay, so that's case 1. It's already a big calculation. I'm not going to do case 2 in full, but let me just mention this, and then I'll start summarizing this in theorems. There's case 2 and case 3, which are just two boundary conditions that will give you a Sturm-Liouville operator with these orthogonal Bessel functions. Okay, so another one that we can choose is that you can have h jn of alpha b, so some constant, so h is a positive constant, times the nth parametric Bessel function plus alpha b. Okay, so this one is specific. So you're on the interval 0b and you're choosing the derivative coefficient to be precisely b. Okay, but h is flexible. It can be whatever you'd like. All right? So again, there's going to be, infinitely many I, okay, with alpha IB roots of this equation. Okay, notice they're not going to be the same as the original alpha I. Those would just make the first function equal 0. Here we're asking that the function, when I plug it in, plus something times its derivative of the parametric Bessel function is equal to 0. Okay, so you'll have different alpha I. They'll still be values. The eigenvalues will again be alpha I squared. Okay, and what we're going to end up with is that the value here, so the norm of the eigenfunction, the corresponding eigenfunction squared, is equal to alpha I b squared minus n squared plus h squared all over 2 alpha I squared times now the nth Bessel function at alpha IB. Remember, this is, as I said before, this is not a root anymore. It's a non-zero value, and so will this one. Okay, so that's the new formula for what the norm is when you have these different boundary conditions. Again, this isn't the craziest calculation. In fact, you can do it on your own. Let me just pull up to where we had. So you would like to work with this equation, okay? And what you're exactly going to be able to do, before we were able to use the fact that this red part all went to 0, well, now we have built this relation between the derivative, which goes here, and the function value, which goes here. Okay, so what you do is you plug this relation into that expression, and you end up with that expression for the norm. Okay, so that's how all of these different cases work. Let me say, okay, well maybe I won't say the last one, and I'll just summarize it in a theorem. Okay, so we'll summarize what we have done so far. So summarizing. So let me say theorem. We're going to have a Fourier, this is really a theorem / definition, okay, of a Fourier-Bessel series of a function value on this closed interval 0b, okay? We're going to write f of x as a sum, so it's going to be the sum I equals 1 to infinity, ci, and then the parametric Bessel function alpha ix. Okay, then if the boundary conditions, so case 1 was if the boundary conditions jn of alpha b is equal to 0, so we got these alpha ib being 0. This was the ith root of the Bessel function. Okay. Then we get that ci is equal. So remember, we have to invert now by the norm of what we computed. So instead of b squared over 2, we're just taking the reciprocal. So we get 2 over b squared times the n plus first Bessel function squared at alpha ib. Okay, that's the norm of the eigenfunctions. And then the good part is it's always easy to remember the inside part of the series. It's just the inner product of the function, ith parameter, and then weighted by this function x, oops, not equal to 0. That's what the formula for the coefficients are. Okay? Case 2, so we now have the new boundary condition is h times the nth Bessel function at alpha ib plus alpha ib times the Bessel function derivative is equal to 0. Notice these aren't the same. I put this in as alpha ib, but these alpha i's are now solutions, which make this equation become satisfied. Okay. Then ci is equal to 2 times the parameter divided by this big mess, fi squared b squared minus n squared plus h squared times derivative, the square of the Bessel function at alpha ib. Again, I know I'm just belaboring the point, but this is non-zero, okay, because of our condition, okay, because of our boundary condition. These aren't the roots anymore of your Bessel function. And the same integral as always, so f of x, nth Bessel function, x dx. Okay? Okay, and finally, let me tell you without any justification, okay, the last case, it's only the case where you have the 0th Bessel function. So actually we're setting n to be equal to 0, and you also set h equal to 0. Okay, so we're just asking about the derivative of the 0th Bessel function. So it's the same boundary condition as just saying this. It's a special case, actually, of what we wrote in 2. but the 0th Bessel function is different enough from the remaining ones that it's good to separate it out. Okay, so this should be equal to 0. So then here you have f of x is equal to c1 plus the sum from I equals 2 to infinity. So it's it's the only one with constant term rather than just something times the Bessel functions. Okay, so you write it as the 0th Bessel function of alpha ix, and the so c1, is equal to 2 over b squared integral from 0 to b of x, f of x dx, okay? And ci is equal to 2 over b squared times the 0th Bessel function squared of alpha I b, okay? So if you plug in h squared and n squared into this expression, you'll get exactly, into this expression, that's what you'll get here. And then you get the integral from 0 to b of x, f of x, j0 of alpha ix, dx. Okay, so it's really, a special case of part 2, but the 0th Bessel function is a little different than the others, so we just separate on this third case. Okay? So let me tell you the theorem, this was really a definition, though it was a lot of work to work out what the coefficients are. The real theorem is convergence of these Fourier-Bessel series, which I'll call FB series. So it's similar to Fourier series, the theorem. So here's what you need to assume. So suppose that f and its first derivative are piecewise continuous. Okay, so we're still allowed to have finite jumps here. Oops, not on AB. That is on the interval 0b. Okay. Then, well, again, you won't get convergence on the closed interval, but for x in 0, so I said that, 0b, the Fourier-Bessel series converges to f at a continuous point and again, similarly to Fourier series, to the average at the discontinuity points, so at the discontinuous points. All right, so that is the theorem. That's what we now want to use. It turns out, let me just look at that. I mean, it seems like our coefficients are much worse than Fourier series, right? I mean, for Fourier series, we saw on your homework that, you had to integrate something like, f of x times the sine of x. Maybe that's a little hard to work with, but you could do it. Here you have to integrate Bessel functions. That seems much harder. On the other hand, there are all these relations between relating Bessel functions to their derivatives, and it turns out that means that integrating Bessel functions isn't too much harder than integrating sines and cosines. So let's do an example here. So computing FB series of f of x is equal to x from 0, let's say between 0 and 3, okay? And what we're going to do is look at, I can choose any Bessel function that I want, so I'll just choose the first Bessel function, and I'm going to assume that the easy boundary condition is satisfied. So this is case 1, Okay, so what do we do? Well, we have a formula for the coefficients. All right, so we get C1 is equal to 2 over 3b squared, so 3 squared times the second Bessel function, evaluated at 3 alpha I. Remember, these are alpha I now. I have to know the zeros of the first Bessel function that, a computer can work out quite easily. I'm just going to leave it as alpha I. Okay, this is what gives us that J1 of 3 alpha I is 0. From 0 to 3, and then we're looking at the integral of x squared times the Bessel function at alpha ix. Okay, so notice we have an x squared here because our function is x and we're weighting with respect to this weighted inner product. Okay, so first let me let t be equal to alpha ix just to do this use substitution. So we get dx is equal to dt over alpha I. Okay, and x squared is equal to t squared over alpha I squared. Okay, so what do we get now? So we get C1 is equal to 2 over 9, and then we have an alpha I coming from the dx and an alpha I squared coming from the x squared, so we get alpha I cubed all times this Bessel function. Okay. We're going to integrate now instead of between 0 and 3, we're integrating between 0 and 3 alpha I. And then we have t squared times the first Bessel function at t dt. Okay? And now we use the nice relation between these Bessel functions. If I take t squared times the first Bessel function, it's the derivative of t squared times the second Bessel function. All right? And what this means is now we're going to integrate this derivative. So we get exactly 2 over 9 alpha I cubed, second Bessel function, just the same coefficient out in front. And then we're integrating t, so we just get t squared times the second Bessel function at t, evaluated at 3i and 0. Okay? Well, now we know that plugging in 0 just will give us 0. And we're plugging in, we get that from the t, or the fact that the Bessel function at t evaluates to 0. So let's see, so we get a j2 of 3i divided by j2 of 3i squared. Here we get, oh, sorry, this is not 3i, 3 alpha I. Okay? So now we're getting a 9 alpha I squared divided by 9 alpha I cubed. So we're ending up with 2 over alpha I. Here we have a j2, the second Bessel function evaluated at 3 alpha I divided by the second Bessel function squared, Bessel at 3 alpha I. So we just get the second Bessel function at 3 alpha I. Okay? And that's it. Therefore, the function that we want, which is just f of x equals x, at least on this interval, is equal to 2 times the sum of 1 over alpha I, Bessel function at 3 alpha I. And then remember, the coefficients, you're writing it as a sum in terms of the first Bessel functions. That was what we chose. Okay, so you just get alpha ix. Okay, so it was a lot of work working out these coefficients. It's a decent amount of work working out the integral, but at least now we can write the function that we would like as this weighted sum of Bessel functions of the first kind here. Okay? And the coefficients will here depend on the Bessel functions of the second kind. And of course you might say this is, why are you writing x in this crazy way? Well, it turns out, as we saw with the wave equation, you start with a simple function and you try to write it as a sum, a weighted sum of functions which are solutions of the differential equation that you might be interested in. Okay, so let me see. All right, so I'm at 45 minutes now. I think I'm going to stop here rather than get into anything else because it's a pretty technical video. So let me just say keep having fun on break / I don't know, do good work. All right.